This video is going to go over a few more examples from section 12.4. In this example, we want to find the unit tangent vector and the principal unit normal vector for the vector valued function given by r of t equals a vector with components t cubed and 2t squared at the time t equals 1. You can use a graphing calculator to sketch the path and determine where t equals 1 would be located on the vector valued function. So using parametric mode on your graphing calculator, you go to the y equals and you enter x equals t cubed and y equals 2t squared. I started off with a standard zoom and then I adjusted the window so that I can get a better, more complete graph. And for my window, I changed the t-min to -5. So you see a portion of the graph, and then I zoomed in over here to where t is equal to 1. When you graph and you press trace at t equals 1, you'll see the location on the path is the point 1, 2. So that's going to be our point right there. We want to find the unit tangent vector and the principal unit normal vector at that given point at t equals 1. So to find the unit tangent vector and the principal unit normal vector, we'll first use the formula for unit tangent vector. You can pause the video now, try this on your own, and then come back and compare your results. For the unit tangent vector t of t, we take, we're going to take r prime of t and divide by the magnitude of r prime of t. Okay, so t of t, the derivative of the vector valued function r of t is 3t squared, comma 4t. Now we're going to divide by the magnitude of that, so that would be the square root of 9t to the fourth plus 16t squared. Now this can be simplified, but for the purposes of this example, I'm going to go ahead and leave it as it is, and then plug in the value for t equals 1. So the unit tangent vector at t equals 1 can be found where the components are 3, 4 divided by the square root of 9t to the fourth and 16t squared. When t equals 1, square root of 25, which is 5. So the components, if you divide each of those by 5, of the components of the unit tangent vector has components 3/5, 4/5. And you can sketch that on the path that I have here at t equals 1. The original location is the point 1, 2. The components of the unit tangent vector would be going 3/5 to the right, 4/5 up, so it is a vector that is 1 unit long, tangent to the path. Now to find our principal unit normal vector, n of 1, we have to reverse the order of the components so that we get 4/5 and 3/5. But we also have to change the sign of one of those. And the principal unit normal vector does point towards a concave side of the path. So in this example, it would be going down and to the right. So the first component would be positive and the second component would be negative. For this example, we want to find the unit tangent vector and a set of parametric equations of the line tangent to the space curve r of t, which is equal to a vector with components t squared, t, 4/3. So our unit tangent vector is our capital T of t. Again, you can pause the video now, try this one on your own, and then come back to the video to check your solution. Our unit tangent vector is r prime of t divided by the magnitude of r prime of t. Now, I didn't sketch this one. It is a space curve. But you can go ahead and continue this without having the sketch. The derivative of t squared would be 2t, derivative of t is 1, and the derivative of 4/3 is 0. So that's a component of r prime of t, and we're going to divide by the magnitude. So the derivative magnitude of those would be 4t squared plus 1. We can divide each of those components by the 2t, so we get, or we can just leave it as it is. Alright, now we've got this far, and I have to apologize for not giving you the entire set of instructions here. I missed a part that said the actual point on the space curve. So let's suppose our point, again I apologize for omitting this, but this should be included when you're working out these problems. Suppose the point has coordinates 4, 2, and 4/3. Okay, this is a point, and the point's given using the coordinates x, y, and z. So to determine the time, you want to look at the variables here, how the position vector valued function is defined, and x is equal to t squared. If x is equal to t squared, and your x is equal to 4, then you could say t is equal to either plus or minus 2. Well, if you look at the what y is equal to t, and on the point y is equal to 2, so we can verify that the time here should be the time at t equals 2. So let's go ahead and plug that into the unit tangent vector to come up with the components of the unit tangent vector. So capital T of the time 2, again that will be given to you either a point or a time, and you're going to use that to come up with the solution. T of 2 would equal to, plugging in 2 for t, we get the vector with components 4, 1, 0, and we're going to divide that by the square root of t squared. That would be 4 times 4, 16 plus 1, the square root of 17. So your unit tangent vector can be written in this way, or you can divide each of those, 4 over square root of 17, 1 over square root of 17, and 0. So that would be the unit tangent vector to the space curve at the point 4, 2, 4/3. Now to find a set of parametric equations for the line tangent to the space curve, we're going to use parametric equations in the form of x, which is equal to, let's extend the page, x is equal to some starting point plus a t, and we've already used t in the parametric equation in the vector valued function, so we're going to use another variable, we can call it s. Y is equal to y sub 0 plus bs, and z is equal to z sub 0 plus cs. There's an infinite number of ways you can come up with a parametric equation for the line. All you need is a point and a parallel vector. We can use the unit tangent vector as the components a, b, and c, and you can use the point for your x sub 0, y sub 0, and z sub 0. That's one way to do that. Again, these are not unique. There's an infinite number of ways you can do that. Let's use the components of the unit tangent vector and the point given. So we would have our x would be equal to 4 plus 4 over square root of 17s. Our y would equal, our initial y was 2 plus 1 over square root of 17s, and our z would equal our initial z, which was 4/3 plus 0s, and that would be simplified to this set of parametric equations. Again, this is not unique. There are many ways that you can solve to get the correct solution here.